Hello. Today's lecture is going to be about buckling of compression members. And when we talk about compression members, we mean any mechanical element that is under compressive loading. In mechanical component jargon, people usually talk about either a column or a strut or a beam column. So all of these are kind of variations of members that can actually undergo very large deformation at some critical load, and is very dangerous to in design applications to be in this situation, so we try to avoid it. The difference is that when we speak of a column, we mean a very thick cross-section and very short member, and the columns exist in various structural elements. They carry tremendous compressive load, and they're designed to be stable. If we have the column a little bit longer, and it may have some transverse loading as well. If there's some transverse loading that can cause some bending, not excessive bending, but some bending, then we would speak about this as a beam/column, which means a combination of column action and also beam bending. And finally, when we talk about a strut is a member that's usually is always in compression, as a matter of fact, and it is more slender than a column. In other words, it doesn't have the same thickness as a column, and it could be in some inclined angles, such as in, let's say, trusses, that you have some members that we can call struts. So that's the subject that we will discuss today in the variety of applications, and we want to determine the critical conditions under which such members can or would undergo buckling deformation. In these cases, we are interested in understanding buckling of compression members, as I mentioned here, and those members can show you here that you could have a variety of possibilities for these members, and they can have different end fixity effects, as you will see here. I'm trying to get this to fit within our window. I think you can see it here better. So under these conditions, the end can play a big role in the stability of the component, and we may have one of four cases. We may have the end being pinned from one end and also pinned from the other end. Of course, if you apply a load on top, then the top pin must be free to slide up and down, and that can cause deflection, and the deflection here, we're going to call it Y. So if that's the case, then we would have to consider what is the critical load that will make this column deflect uncontrollably. The second possibility is that one end would be totally fixed, so it doesn't allow rotation on that end, and the top part of the column is still pinned but free to slide. And in this case, you can see, because one end is fixed, then it should resist buckling a little bit more. Third case is when one end is fixed and the other end is totally free, and in this case that's kind of a more dangerous situation, because the member can buckle very easily. And then finally, the last case is that one end is fixed and then the other end is free to slide, pinned here. So all of these are possible buckling situations that we will discuss. And the idea now is that we are interested in defining the critical buckling load for these situations. And the critical buckling load, the idea is very simple, is that we know that the curvature of the beam is proportional to the local moment on any section. So the curvature is the second derivative of the transverse displacement, y, double prime. If the moment is somehow related to y, then we have to study whether the moment will increase with the deflection or decrease with the deflection. In all of these situations that you see here, the distance of the neutral axis y is such that the moment, the local moment, is just simply the axial force times that distance y. In other words, as the beam deflects more, the moment increases. And therefore, we get a second order differential equation. We know that deflection equation, second order differential equation that has y double prime, and then you have the moment now over EI, which is P times y. So you get an equation like this, y double prime plus P over EI times y is equal to 0. That's kind of the deflection equation. This deflection equation is the solution to this is very simple. It's sine and cosine, and it has a wavelength, and the wavelength is determined by this quantity P over EI. And also, other aspect is that by the end boundary conditions that determine that. So the result of this is that we can compute the critical load that will allow this column to buckle in an uncontrollable manner as follows. So I'll just start here and write the main equation. It's called Euler formula. An Euler formula is given by the critical load is equal to a constant times pi over the length of the column squared times EI. Note that, as I wrote before, P over EI appears here in this equation right here, and that when P is a critical value, that you have some kind of matching with the boundary condition, then you get the critical buckling load. And C now is a constant that depends on the boundary condition. So C is equal to 1 if we have pinned ends, two ends that are pinned. C is equal to 4 if we have one end that is pinned and one end that is fixed. C is equal to 1/4 if we have one end that is fixed and the other end is totally free. And C is equal to 2 if we have one end that is fixed and the other end is pinned. So these are the conditions that come from the boundary conditions, and therefore we could use that to tell us the critical load that will cause buckling. Usually this equation is sufficient to calculate the critical load, but we will just kind of develop it a little bit further to cast it in a form that is suitable for calculations of the actual stress in the column by dividing the critical load over its cross-section area. So to go there, we have to follow a couple of steps. First is that we have to define a new quantity and this new quantity is called the radius of gyration, and is defined in such a way that the second moment of area is equal to the actual area of the cross-section times the radius of gyration squared. So k is the radius of gyration. The reason we do this definition is that, number one, it came from dynamics of rigid bodies, radius of gyration, the member, if it moves, then it moves with that radius. Number two, it's really useful because we can convert the second moment of area to a cross-sectional area times an effective radius squared. So with that, I can write now the Euler equation in a slightly different form, that I can write it as P critical, and if I define it by the cross-sectional area, I would be able to call this the critical stress, and that would be equal to the end fixity constant times the elastic modulus times pi, instead of L squared, be L over K, and that is squared. And note that it used to be E over I down here, but that we got rid of the I by writing it as A times K squared, and that's how we ended up with this type of formula here, where we write the critical stress directly. Obviously, this critical stress, if you try to plot it as a function of the length, so basically you have a relative ratio of the length of the column divided by its radius of gyration as kind of a non-dimensional quantity. So if you try to plot against that quantity, you will get a hyperbola. So it looks like this. So if I have L over K, I define it like, let's say, X, for example. And then I have sigma crit is equal to a constant times E times pi over X squared. So this is, all of these are constant, and if I need to now plot it as a function of X, then the critical stress is going to obviously decrease as a function of X in a kind of a hyperbolic fashion. So as X increases, then so is the critical stress. And X is no more than L over K. This is the non-dimensional size or length of that column. So if you look at this behavior, then you see that we can get some real problems if we have L over K to be small, and because the stress can exceed the yield point of the material. So we're going to define L over K as the slenderness ratio. So X now is the slenderness ratio, and there has to be kind of a limit on how slender the beam, the column is going to be before it actually yields. So it can yield or buckle depending on whether the critical stress is below the yield point or above the yield point. So the L over K is a slenderness ratio. This is slenderness ratio. It must have some kind of limit, because at some point here, then the material is going to yield. So we don't want to even go close to the yield, so we want to limit this Euler formula up to the yield strength of the material over 2. And therefore, there's kind of a value here, we're going to call it L over K sub 1, such that at this point, we're going to call it T. At point T, the critical stress reaches half of the yield point. And this region here of the curve, which goes from point T all the way to infinity, is called the Euler curve. So we're going to just call this the Euler curve, which defines the relationship between the critical stress and the slenderness ratio. Now, that is fine if we just wanted to check on the ability of the material to actually undergo buckling or undergo yield. So we're going to see if we have another condition to protect against yield completely. So if we have now, let's replot this curve here. We're going to have on this side, these are the two axes, and on this side here I have L over K. This is my x-axis. My y-axis is sigma crit. This is the critical stress for buckling. So on here I have a basic curve that is described as a hyperbola, but we're going to take the point T here, and this point T is what we defined before, such that I have L over K sub 1 here, and I have half of the yield point S yield over 2 in here. Now, as we can see that for a smaller slenderness ratio, like if the L over K is really small, then we may actually have a yield condition, and therefore we want to protect against yield rather early. So in this region we introduce another behavior that will govern the design such that we do not allow the critical stress to go anywhere near yield. So we know basically that at some point here we have the yield point. If this is S yield, for example, then between S yield over 2 and S yield we cannot follow the black curve. Then we introduce another curve that is a parabola, and this parabola here is more conservative than the Euler curve. And this parabola here is called the Johnson parabola, and it is empirical because it guarantees that we don't, the critical stress for buckling does not exceed the yield, and the parabola can be determined from the coordinates of 2 points. One point we have S yield and 0, like the L over K is 0, and the other point is the coordinates T, which is the X coordinate is L over K1 and S yield over 2, and the coordinates of point Q, this is point Q here, is 0 and S yield. So I have two points with each one we know the coordinates, and we describe a parabola to pass through 2 points with their given coordinates, and that will define completely the green curve as a Johnson parabola. So now I can write it in the following form. If I just find the parabola, then it would be it would look like this. The Johnson parabola will be written as P crit over A, which is sigma crit, sigma CR, is equal to a constant A minus another constant B times L over K squared. That's the formula for a parabola. And then A and B are constants that I can determine from the coordinates of these points that I mentioned, point T and point Q. So in this case, I can write it in such a way that the point A and B, the constants A and B, are completely defined, and in fact A is equal to just S yield, and the constant B, when we work it out, we find it to be S yield over 2 pi, and this is all squared, 1 over C times E. So these are the values of the two constants, and these two constants are valid for the parabola, and therefore the parabola, the Johnson parabola, sigma cret, is equal to A minus B times L over K squared, and that is for values of L over K less than or equal to L over K1. Okay, this is L over K1 is the limit. L over K1 is the limit above which we would apply straightforward Euler formula, below which we would apply the Johnson parabola for buckling design. However, we also want to kind of redraw the entire curve with everything that we mentioned here for design. So in this case, we would have to use the axes again as the x-axis and y-axis, as I mentioned before, and in here we would have two segments of the curve. One segment is not defined below a certain point, and then defined above a certain point, and then the other one is takes over from here and then continues on to be parabolic shape here. So the points that we have are point T, and this is a point Q. So Q is this point and T is this point. So point T is at the horizontal axis at L over K sub 1. So we have found that. And point Q, it has a value of L over K sub Q, and that is when the yield point, the vertical yield point, is equal to the value of the critical buckling stress. So this is Euler here, the green is Euler, and the red is Johnson. So beyond that point, beyond this, we are able to make the design, and I'm going to give an example to show how this works in selecting the diameter to protect against buckling, or in finding out if a given configuration or cross-section would undergo buckling. So let's look at an example here. So the example we have is as follows. We have now, let's see, we have and here we just defined all of this, the critical stress with the parabolic curve for points T and Q, and L over K 1 and L over K sub Q. So we define all of that, and then we can find from just the coordinates that the value of L over K sub 1 is actually equal to this value here, 2 pi squared CE over S yield, from equating half of the yield point to, like S yield over 2, half of the yield point to the value of sigma crit. So this is the equality. Then we can find L over Q1. Similarly, if we equate the full yield to the critical stress, then instead of S over SY over 2, then we just we'll have no factor of 2 inside this formula. So we now have a pretty good idea about the entire behavior. and therefore we can take it for design applications. And here is again more of a summary of the entire design process with the Euler curve and the parabolic curve. And the parabolic curve has a shape, and we wrote down the A and B for that, and then the range of validity as well. So let's now skip that and then just go straight to an example. So the example, first example is we want to develop specific Euler equations for the size of cones having round cross-section and rectangular cross-section. So the round cross-section, first we're going to have to write the area and find the radius of the gyration, square root of I over A. I is equal to pi d to the power 4 over 64 for a round cross-section. And then the area is pi d squared over 4. We take the square root. So the radius of gyration is just 1/4 of the diameter. And therefore, we can find that the diameter that will cause a critical buckling is given by this formula here. In other words, this is the condition such that sigma crit is equal to, so it depends on the end fixity effect, so we have to include the factor of C. So we have C times E, and then we get pi over L squared, and then from that we can obtain the diameter for the critical value that will cause buckling. So if we go back to equation 444, we will find that this is the actual diameter from the calculations. So now if we look at critical cross-section, so before we do that, let me just kind of go back to review this before we go to the actual cross-section situation here, where we have like a rectangular cross-section. The Euler curve is here, so we have B critical over A is equal to C times E, and then I have pi squared L over K squared. And K, when I have for the a round cross-section is D over 4, then I put it here, and then I for a round cross-section is pi D to the power 4 over 64, and keep the C in because it depends on the end conditions, and that will give me basically the critical diameter for buckling. And I can do that also for the rectangular cross-section. Now the problem with the rectangular cross-section is that you have a B and an H here, so it depends on which one is larger than the other. Of course, buckling if you just buckle against the H, then that's much harder than buckling of a very thin piece of wood like this, and then you are trying to apply the moment this way. In other words, it depends on the moment axis, and here the moment axis, if it is passing through H, where H is the largest of the two, then it will be harder to buckle. So you have to look for the smallest value of the two aspects of a rectangular cross-section. So going back to the problem at hand, we see that for a rectangular cross-section, this is I, and this is A, and the K squared is I over A. It turned out to be H squared over 12. And when we substitute, then we get a critical value for B, and this is critical value is obtained when H is less than B. If H is greater than B, then we just reverse the roles of B and H in this equation. So in this example, we illustrated how to find the critical dimensions for buckling. Let's now look further. There's another example here where we want to specify the diameter of a round column, 1.5 meter long, and it is to carry a load of 22 kilonewton, and we have a design factor of safety of 4. And we want to consider the ends as pinned, so pinned is rounded, the same word, and we're given the yield strength and the modulus of elasticity. So this is a complete design problem. So in this problem, we are given the load, and then we're given a factor of safety. So when we're given a factor of safety, one easy approach is to increase the load to be on the conservative side. By if we multiply the load by the factor of safety, then we are just imagining that the load is say n times what it is. So in this case, the load is 22 newtons, the factor of safety 4, then we would make it 88. So, and then start using the formulas that we have talked about before. And the n fixed effects, C is equal to 1. And then we just go straight forward first to determine the diameter using Euler formula, and then hope for the best. If we have to check after we find the diameter that the slenderness ratio is it greater than L over K1 or less? If it's greater than L over K1, then using Euler formula is correct, and the result is acceptable. If it turned out to be that L over K is less than L over K sub 1, then we should reject the Euler curve and then use the more conservative Johnson parabola in the design. And that's exactly what we'll do here. So if you look here, then I have first the load is increased to account for the safety factor. Now we use the previous results with C equals 1 to find the diameter to be 37.48. And I have one word here that if you calculate a diameter and it comes to be fractional, that doesn't mean that the design is finished, because you have to look in the tables for the preferred sizes. Because when you go out and buy or order rods, for example, then we cannot order a rod that has a diameter of 37.41 millimeter. It has to be the nearest, and the nearest we always round it to the highest value, and that is in this case 40 millimeter. So if you go to the table A17, then it gives us the preferred size to be 40, and then we start testing. So we test here for Euler, and then when we test for Euler, then L over K is L over D over 4. It turns out to be 150, and then we want to find L over K sub 1, and L over K sub 1 is obtained by equating half of the yield point to the critical stress, and that comes to be 90. So since 150 is greater than 90, then we are safe and the design is acceptable from a standpoint of Euler. Of course, you can have other problems where this is not the case and you have to follow the Johnson parabola to complete the design. Okay, I think this is what we needed to cover on buckling. I have just one additional small topic that I'm going to cover, which is shock and impact, and give an example of how to do the calculations for impact, the deflection due to impact loading and not to a static loading. As far as we've seen here, all of our work has been on static loads. But what happens if the load is not directly in contact, but it's actually falling on the beam? How do you do that? How do you figure out the load? We know that the load is obviously going to be, effective load is going to be bigger because it's dynamic. You have some inertia in there. So the method we use is going to be simple. We're going to take, if we have a falling object on a surface, a beam, then we calculate the potential energy, and then we're going to assume that there's no momentum transfer to make our life easier, so there's no bouncing back and forth and momentum transfer. It's just we want to convert, get an idea, so we want to convert the potential energy to actual deflection energy. Like there will be no kinetic energy. We're going to ignore that, the vibrations, but we just have a deflection that will absorb the impact energy due to whatever, if it is falling or if you're shooting something at a surface, then you can also convert the kinetic energy to an elastic deformation energy. Same concept. So let's look at one example before we finish this lecture. And in here, I'm going to have a situation where I will decide now, let's just go directly to the impact idea and look at this situation. So in this situation, you have a load, and the load is falling a distance h, or it could be a bullet, for example, for that matter. In the case of a bullet, you have kinetic energy. In the case of a falling load, you have potential energy. In either case, this is converted to some kind of elastic energy that will be stored in this beam that has EI and L as characteristics. So let's consider a spring. A beam is like a spring. So this is a simple case. And the beam, let's say, has an effective stiffness K. Once we just find, if you have a certain beam, then you find the effective stiffness, which is F over Y. Okay. So in this case, we have a beam. The beam is supported from one side, and then you have a force on the other side. Then the Y deflection is equal to L cubed over 3EI. And you have here F. So this is the Y deflection. So if you just calculate F over Y, you get 3EI over L cubed. So if you have a different kind of beam, then you have to do this calculation to find the relationship between the force and the deflection under the force, and that's an effective spring stiffness that we will use. Having done that, then we deal with the beam as a spring. So in the spring here, I have the potential energy is W times H plus delta. The potential energy in compressing the spring is K times delta squared over 2. And therefore, conservation of energy, this is the elastic energy stored. Elastic energy stored. If we equate the elastic energy stored to the energy of the potential energy of the falling object, then we find that we have a second order equation, algebraic equation in delta. And we solve for delta, we find that we have actually two values for delta. The maximum deflection is with a positive, so the maximum deflection that we would have here is given by W over K plus W over K times 1 plus 2HK over W all to the 1/2. And the maximum force is multiplied by the spring stiffness K to give us that maximum force that we can use for design applications. So if I have a design application where I have an impact loading, let's say a mass impacting on a car, and I'm able to determine the kinetic energy of that mass, convert it to, and then find if the car bumper is like a beam, then I can find the elastic stiffness of that, equivalent elastic stiffness of that beam, consider it as a spring, then I'm able to compute the maximum force due to the impact, which is a very useful formula that I have. So this is the maximum force. Of course, this is approximate because we ignored any dynamics in this situation and is basically quasi-static calculation. However, this can be very useful because if I have a finite element solver, I can use this force and then determine deformations or approximate deformations in the member. So we have now all of the ingredients that we require to calculate deflection of various forms, either beams, indeterminate beams, curved beams, and so forth. And we are able also to compute very large deflections due to buckling. And the buckling can be elastic or can lead to plasticity. In the case of plasticity, then we use the Johnson parabola. And finally, if we have a dynamic load, how to convert this dynamic load to an equivalent static load and do deflection calculations for it. And with that, we're going to